It is the winter of 1976, and Colin Chapman is staring at a problem that has been sitting in front of every Formula One designer for a decade without anyone fully solving it. The problem is simple to state and brutally difficult to answer. Wings generate downforce, but wings also generate drag, and drag costs speed. Every kilogram of downforce you add with a wing costs you something on the straight. The faster you go, the more you pay. The entire history of Formula One aerodynamics since 1968 had been a negotiation between these two competing demands: more grip in the corners, less resistance on the straights, and nobody had found a way to escape the trade-off. Chapman believed he had found the escape route. By the time you understand what he built into the Lotus 78, you will understand why Mario Andretti said the car felt like it was bolted to the road, and why the FIA banned the principle that made it work, only to watch it return 45 years later as the foundation of the most technically sophisticated Formula One cars ever built. This is the story of ground effect, the aerodynamic breakthrough that changed what Formula One is and what it is still becoming. To understand ground effect, you need to understand what was already known about air moving through confined spaces. The principle had been established by Daniel Bernoulli in the 18th century and had been applied to aircraft wing design for decades. When air is forced to accelerate through a narrowing passage, its pressure drops. Low pressure pulls things toward it. This is why aircraft wings generate lift. The upper surface of a wing is curved, so that air traveling over it moves faster than air moving beneath it, creating lower pressure above and pushing the wing upward. Chapman's insight was to apply this principle in reverse and in a completely different orientation. Instead of generating lift, he wanted to generate downforce. Instead of using a wing above the car, he wanted to use the space between the car's floor and the track surface as the narrowing passage. If you could shape the underside of the car correctly, if you could create a Venturi tunnel that accelerated the air flowing beneath the car and reduced its pressure, the atmospheric pressure above the car would push it downward. The ground itself would become a wing. But instead of lifting the car into the sky, it would pin it to the earth. The concept was not entirely original. Aircraft designers had observed ground effect, the tendency of wings to generate additional lift when flying close to a surface, since the earliest days of aviation. Racing car designers had speculated about exploiting the underfloor for downforce since the late 1960s. What Chapman did that nobody else had managed was to solve the practical problem that had stopped everyone else. How do you prevent the high-pressure air surrounding the car from rushing in underneath and destroying the low-pressure zone you are trying to create? The answer was the skirt, a sliding seal made initially of a ceramic-coated fabric and later of more sophisticated composite materials that ran along the bottom edge of the car's side pods and maintained contact with the track surface. If you could seal the underfloor from the surrounding atmosphere, if you could keep the high-pressure air out and the low-pressure zone intact, the downforce numbers became extraordinary, not marginally better than a conventional wing arrangement, categorically better. The kind of better that makes the timing screens look like they are malfunctioning. The Lotus 78, which appeared for the 1977 season, was the first car to incorporate these principles in a form that worked on a race circuit. Its side pods were not side pods in the conventional sense. They were carefully shaped aerodynamic tunnels, their inner surfaces forming an inverted wing profile, their lower edges fitted with the sliding skirt system that Chapman's engineers had spent 2 years developing and refining. The radiators, which in a conventional car of the period occupied most of the side pod volume, were repositioned and resized to leave as much of the underfloor channel clear as possible. Every packaging decision in the car had been subordinated to the aerodynamic requirement of making the Venturi tunnels work. The results in testing were, to Chapman and his engineers, simultaneously thrilling and alarming. The downforce figures were unlike anything they had measured before. At 160 kilometers per hour, the Lotus 78 was generating more downforce than cars with far larger rear wings. At 200 kilometers per hour, the numbers were becoming difficult to believe. The car was being pushed into the track surface with a force that its suspension had not been designed to handle, and its tires were generating grip levels that were operating at the edge of what the rubber compounds of the period could sustain. Mario Andretti, who drove the Lotus 78 in 1977, described the sensation in terms that other drivers of the era found difficult to reconcile with their own experience in conventional cars. The grip did not build gradually as speed increased, as it did with conventional aerodynamic downforce. It arrived in fast corners at the speeds where the ground effect was fully developed. The car felt as though it had been physically pressed onto the track by a force that had no mechanical explanation a driver could identify. You turned the wheel, and the car went around the corner at speeds that should have produced understeer or snap oversteer in any vehicle that obeyed the normal rules of physics. The Lotus 78 did not obey the normal rules. It had found a way to generate grip from the track surface itself. Andretti won 4 races in 1977 with the Lotus 78. The car was not yet fully developed, the skirt system was imperfect, the aerodynamic ceiling was inconsistent, and rivals were beginning to understand what Chapman had done and to develop their own responses. But the direction of travel was unmistakable. Whoever solved the practical problems of ground effect implementation most completely would have a fundamental performance advantage that no amount of engine development or conventional aerodynamic work could close. Chapman solved them with the Lotus 79. The Lotus 79, which appeared mid-season in 1978, was the Lotus 78's principles taken to their logical conclusion. Where the 78 had been a ground effect car that still retained some conventional aerodynamic thinking in its design, the 79 was a ground effect car from first principles. The entire car had been designed around the Venturi tunnels. The side pods were wider and longer, creating larger and more efficiently shaped channels. The skirt system was more reliable and more consistently sealed. The rear diffuser, the section of the underfloor behind the engine where the accelerated air was allowed to expand and recover pressure, was more carefully developed to maximize the energy recovery from the airflow. The car was, as an aerodynamic object, more coherent and more complete than anything that had raced in Formula One before. Andretti dominated the 1978 season in the Lotus 79 in a way that the statistics alone do not fully capture. He won 6 races. He led more laps than any other driver. He clinched the World Championship before the season had concluded. But the numbers that tell the real story are not the race results, they are the qualifying times. At circuits where ground effect worked well, smooth, fast tracks with consistent surfaces that allowed the skirts to seal properly, Andretti was not a tenth of a second faster than his rivals, or 2/10, or even half a second. He was lapping in times that placed him in a category of performance that seemed to belong to a different technical formula. Other drivers, in cars with ostensibly comparable engines and far from negligible aerodynamic development programs, were not in the same conversation. Stay with this, because what happened next is the part that changed Formula One permanently, and not just for the years that followed immediately. Every team in Formula One had been watching. They had been watching in 1977 when the Lotus 78 appeared. They had been watching more urgently in 1978 as the Lotus 79 demonstrated what a fully developed ground effect car could do, and they had been in their wind tunnels, on their drawing boards, and in frantic discussions with their engineers about how to build their own versions. The problem, as every team discovered in turn, was that ground effect was not a concept you could simply adopt. It was a design philosophy that had to be built into a car from the beginning. It required a specific engine packaging arrangement. The Ford Cosworth DFV V8 that Lotus used was narrow enough to leave room for the Venturi tunnels on either side. It required a suspension geometry that could maintain the skirt contact with the track through the full range of ride height movement. It required an understanding of the interaction between the underfloor aerodynamics and the car's mechanical behavior that no team had needed to develop before 1977, because no team had built a car that behaved this way. Williams, Brabham, McLaren, Ferrari, Renault, all of them spent 1978 and 1979 in various stages of ground effect development. The quality of their solutions varied enormously. Williams, with Patrick Head's FW07 appearing in 1979, produced what most engineers of the period regard as the most complete and reliable ground effect implementation outside of Lotus itself. The FW07 was not faster than the Lotus 79 at its best, but it was more consistent, more mechanically reliable, and better suited to the full range of circuit characteristics the season demanded. Alan Jones won 5 races with it in 1979 and the World Championship in 1980. Other teams struggled. The ground effect concept was unforgiving of implementation errors in a way that conventional aerodynamic development was not. A car with slightly wrong Venturi tunnel geometry did not simply generate less downforce than the optimum. It generated downforce that was sensitive to small changes in ride height. If the car's floor moved even a few millimeters from its design position, the aerodynamic balance could shift dramatically and unpredictably. Drivers described the sensation of the car suddenly losing its front-end grip in a fast corner. Not gradually, not in a way that gave warning, but instantly, without mechanical explanation, at the worst possible moment. This behavior had a name: aerodynamic snap. And it was not a minor handling characteristic to be managed through setup changes. It was a fundamental consequence of operating a car at the edge of its aerodynamic envelope, when that envelope had a cliff rather than a slope at its boundary. The downforce was there, and then it was not. In a slow corner, this was recoverable. In a fast corner, at the speeds that the ground effect cars were now capable of, it was not. The deaths of Ronnie Peterson at Monza in 1978, in an accident that was not directly attributable to aerodynamic snap, but occurred in the context of cars traveling at speeds that ground effect had made possible, and Patrick Depailler and others in the years that followed, created a safety debate that ran alongside the technical one. The cars were faster than the circuits had been designed to contain. The grip levels were higher than the tires had been designed to sustain consistently. The aerodynamic forces were larger than the structures surrounding the drivers had been designed to resist. The FIA's response was gradual, but ultimately decisive. Flat bottom regulations, requiring the underfloor of the car to be a flat surface from the front axle to the rear axle, eliminating the Venturi tunnels, were introduced for the 1983 season. The sliding skirt systems had already been banned for 1981, which had partially degraded the ground effect performance of the cars, but not eliminated it. Teams had responded by stiffening their suspensions to reduce ride height variation and maintain some approximation of the aerodynamic seal. The 1983 flat bottom rule was intended to close the gap completely. It did, for 40 years. What happened in 2022 is the conclusion that the ground effect story had been waiting to reach since 1983. The FIA, responding to concerns that the aerodynamic turbulence generated by modern Formula One cars made close racing and overtaking increasingly difficult, introduced a new technical formula centered on ground effect. The Venturi tunnels were back. The underfloor downforce was back. The principle that Colin Chapman had identified in the wind tunnel at Hethel in 1975 and raced at Kyalami in 1977 was, 45 years later, the official technical direction of Formula One. The cars are different. The materials are carbon fiber rather than aluminium. The computational fluid dynamics tools that designed the floors of the 2022 cars would have been incomprehensible to Chapman's engineers. The safety structures surrounding the drivers are categorically superior to anything available in 1978, but the physics are identical. Air accelerated through a Venturi tunnel loses pressure. Low pressure pulls the car toward the track. The track becomes a wing. Chapman's insight holds. What the ground effect story demonstrates, and what makes it more than a historical curiosity about a particular aerodynamic concept, is something about the relationship between engineering and regulation in Formula One that repeats itself across every decade the sport has existed. The regulations define a boundary. Engineers find the space between the boundary and the limit of what physics permits. The boundary moves, the space opens again elsewhere, and the cycle continues, driven by the same force that drove Chapman to his drawing board in the winter of 1976. The absolute unwillingness to accept that the trade-off between downforce and drag is a fixed condition of the universe, rather than a problem waiting for a sufficiently creative solution. He was right. The trade-off was not fixed. He found the escape route. And Formula One is still driving through it. If you found this useful, subscribe. There are more stories like this one in the archive, and more coming. Leave a comment below. Which breakthrough should we examine next? The blown diffuser that won Red Bull 4 consecutive championships, or the semi-automatic gearbox that made the human hand too slow for Formula One?